Good morning.
I think this morning is not very good. Not too many people are here. I think you're still in bed. So yeah, it's good thing that I'm recording this so then you can review it afterward. For those who cannot make it today, please review the video. Oh, wait, I need to pull that down. Okay, good morning once again. So I'll try to finish this session in 2 hours, and then if anyone would like to discuss the project, we can. So today I'm going to cover the topic of relational algebra and relational calculus. And let me do this. And if you look at the slide, you should be able to get the slide. And then if you may also see the assignments as well. So for the first two assignments, the answer will be posted soon. And then you can check your answer against the key that we'll be giving out. And what you can do, if you can look at the in the announcement about the 3 extra points, you can check, and then if you want to argue that your is a good answer but different from the key, you can, and then you can earn extra point as well. So let's come back to the lecture for this time. It is on relational algebra. But why is it important? Because this relational algebra, if you remember, it was introduced in about 1970 by Professor Edgar Cott, and the basic behind all the commands on the relational algebra and on SQL that you'll be writing comes from set theory. And basically, I put it there that you already learned set theory actually from school, from high school, and also from discrete math. But if you already returned all the knowledge to Ajahn, so I don't know what to do, right? So you have to. Did you return all the knowledge to Ajahn? Who taught discrete math? อาจารย์กุลวดี okay. So you still remember, but it's very basic because set theory you've learned it from high school. But then with the relational algebra, there are some additional constraints on those set theory to be able to calculate whatever you retrieve from the database. So the foundation of these would come from another set of mathematical foundations called relational data model. I mean, it's the theoretical foundation called relational data model and query languages. Let me say it again. The set theory is actually the foundation, okay, that produces relational data model and also the query languages. And beforehand, SQL or query languages was offered long time ago, like I mentioned, but the earliest version is SQL 2023, which allows, the basic of this language is that it allows the manipulation of the data that you have in your database. The earlier version of SQL at the beginning, it wasn't equal to programming languages. Basically, when we talk about query languages, it doesn't have the same power as the programming languages. It means that you can only do something with the data, manipulating the data, delete the data, add the data, but you don't have the whole set of commands like you write programming codes. So it was not equal, it was not equivalent. But then when at that time, so when it is not equivalent to programming languages, we say that it's not Turing complete because again, it doesn't have every command that you can command in the traditional programming language because it was not intended to use for complex calculations, right? But it is intended to be an easy language that you can access the data. However, at the moment, SQL has been further developed such that now it is equal to the programming language and hence Turing complete as well. And if you look at the SQL now, you can look at it as another programming language, but it has a special power to deal with the data in the database. So to have this query language, it is based on two mathematical query languages uh, to form this. One is called the relational algebra, and another is relational calculus. I think I have asked you before, like who like calculus, who prefer algebra, and I think most of you said none, right? So basically, well, you have to do it anyway. But for database or in SQL language or SQL language, it is based on these two. And these two are actually comparable. Actually, they are interchangeable. You can use one or the other. If you use relational algebra, it is operational. It means that it operates one line at a time. So it is sequentially executed. So, when it is sequentially executed, it is appropriate when you want to write or you want to know the execution plan, like you wanted to execute this and then do the next, do the next. Then you will know exactly what it does at each moment. However, if you choose to write relational calculus instead, you can do also, and you will also retrieve um, the same result, but you write the command differently. So in relational calculus, it's not procedural or it's not like one line by line, but it is non-procedural or declarative. So basically you describe the results that you wanted, and then you don't have to write how to compute it one line by line. Let us look at the example. I have an example instances here, and there are three relations: relation student, relation boat, and relation reserve, but student reserves boat, right? I don't know why student reserves boat, but just say that they want to go to a Suan Lum, right? And then Suan Lum has boat for recreational purposes. So for student, I have student ID, which is integer. I have student name, string. I have rating as integer, and I have age as real. And for boat, I have boat ID, it is integer. I have boat name as string. I have color as string. And then for reserve, I want to know which student reserves which boat. So, oh, hold on. I need to turn my phone off. Okay, so to reserve, I need to know which student reserves which boat and on what day. That's why I have the student ID to signify which student. I have BID, which is boat ID, so you know student and boat, and then you have day, right? Now, there are data in each of the relations. For example, for a relation called student, and at one time or at one snapshot, I said that there are three students in there: SID 22, 31, and 58. And you can say that I am a fan of Blackpink, right? So I have Jisoo, Jennie, and Rose, and the rating doesn't matter what it means, but I know that I have the rating for students 7, 8, and 10, and then I have their age in the attribute called age. Now, if you take a look at the student table or student relation at different times, you probably have different data within you can have like different rows of data in the table. So now at instance S2 of student, I have four lines there or four tuples there, Lisa, Jenny, V, and Rose. And then for instant boat B1, I have BID, B name, color, and I have three tuples there, 101, 103, and 105. Now, I also have another relation called reserve, and the instances are one. So for R1, I have student ID 22 reserving the boat 101 and on that specific day. And also student number 58 reserving the boat 103 on another day. So you can see I am going to use this example of instances for computation afterward. All right. Now, first thing first, there is some important note when we are writing. Oh, why do I have it in Thai? Sorry, I should change all the data in to English. Sorry about that. But anyway, I'll change it up right afterward. So the important note on notation is that look at the look at the line there. I said, if you operate between lowercase letters, so I said that if I have an R minus S and I write it in a lowercase letter, then it refers to relational algebra operator, meaning that you minus R minus S. What it means is that, uh, let's say that, see, I don't know how to turn this. Wait, microphone. Okay, is this better? Okay, now, okay. I have, if you take a look at this relation called ENG student, and you have SCI student, engineering student, sci student there, right? So the name of the relation is usually written in an uppercase letter to tell you that it is a relation name. But now, if I want to write an operation, I will do it in a lowercase letter. So I write ENG student in lowercase letter minus sci student in lowercase as well. What it means is that you take the data within the table and minus each other. So let's see here. I have ing student less sci student. So then I only have Lisa, Jenny, and Rose left, and then we was discarded. However, if I write the operation using uppercase letter, it means that we are going to operate on the schema, not the data. All right. On the schema or on the structure of the table, structure of the relation rather than the data within it. So let's see that if I have R, okay, if I have relation R comprises student ID and age, and I have another one, I have a relation S comprises student ID only. Then if I say uppercase R minus uppercase S, then you can take a look at the attributes and you can see that there are the same attribute there, student ID and student ID in two different relations. Then you take the minus and then you only have age left. All right. So to write the operation correctly, if you want to operate on the data within the table, then you use the lowercase. But if you are operating with the uppercase, it means that you are changing something with the structure of the table or the schema of the table, right? Now, another notation that you'll be seeing sometimes that you may have to use it is that if you take a look at these two tables, ing student and sci student, you can see that student name are the same. So if I refer to a student name, I have to say exactly which table or which relation it came from. So I have to use this notation called dot notation. So if you take a look down here, I said ENG student dot student ID. Now I know exactly that I am talking about student ID from the ENG student, not from sci student relation. All right. So dot notation will comprise the name of the relation dot the attribute name. Okay. Okay, so the relational algebra operation can actually be unary or binary, and you can tell it by its name that unary is one, right? And binary is two. So basically, if you operate on just one relation together, it's called unary. If it's two relation instances together, and it is binary, right? And it doesn't matter if you do it of unary or binary operations, the result from the operation will always be in one relation instance. All right, just one relation instance. So operations of for all the relational algebra can be composed together, and if you have many operators, we can call it a collection of operators, right? Now, let's see what kind of operators are there. The first set is called basic operators. So the first operator is called selection. You can see the symbol that signifies selection is a small sigma. So that a small sigma. So sigma is select. You can tell like S and S, right? So what does selection means? When you use sigma or select, it will select some rows or some tuples from the relation. All right. The second operator is called projection, and it is signified by the small pi. So P is projection, pi projection, right? So what projection does is that it doesn't select some row, but it selects the columns or it selects the attributes from the table. The third operator is called cross product. So basically, it's just combines the two relations together. But cross product, let me tell you that it is such a waste operator because I can give you the example later on. But what it does is that it produces a very large table because you cross product between two tables, and then it would produce some errors within it. So when we use cross product, we don't use it just by itself. Usually we will use cross product to do something else. So just keep in mind that cross product by itself can produce a lot of errors in the results. All right. Now, the next operator is called set difference. And by what it means is that it just take the tuples from one relation that is not in another relation out. And then next one is called union. So basically, you union two different relations, then those relations has to be compatible. And when we'll talk about how to make it compatible later on. So these five operators, selection, projection, cross product, set difference, and union are called basic operators, right? Basic operators. The reasons that they are basic because the rest of the operators will actually use the basic operators and combine each other to make up some calculations, all right? So what we do is that what we do is that instead of using just basic operator combining each other, we don't have to do that. So there are some additional operators that you can use and will make life a lot easier. So the first operator that you will see a lot is called join. When we talk about join operator, you use this ribbon, the ribbon notation there. And the next one is called the intersection. And the intersection is just the intersect operator, the division operator, renaming operator. Oops, renaming operator. So join use the ribbon there, intersection, division, and renaming you use the small row, right? RHO row. So that's why R is row, and it is used for renaming, right? So these are the relational algebra operator, and actually they compose the basic operators to form these four. For example, the join command or the join operator here actually came from cross product, then select, all right? And intersection is another set. So we'll take a look at how each one operates. Let's go to the first one, selection. So when you are writing selection in relational algebra, you will say selection or the sigma, and you give a name of the relation here. And then in the subscript, you can tell, you can specify the selection condition. So basically, it will select the row that meets the selection condition here. So basically, the schema of the result will be the schema of the input relation. For example, if the input relation has like 5 attributes, the result would also have 5 attributes, right? Let's take a look at the example. If I have the S2 here, and I have this command, say select from S2 in the back. See, I have a small s because I am operating the data within the table. So I use lowercase here. And then I say, I only select from S2 where rating is greater than 8. So what would be the result? How many rows? Just 2 rows, right? So yeah, that's basically what selection does. Now, selection can also have some condition, right? So condition, you saw on the other slide, on the previous slide, is greater than, but you can use any Boolean combination and terms that have the forms like attribute, operate the constant, attribute 1, operate attribute 2, you can do that, right? And the comparison operator can be equal, not equal, less than or equal to, greater than or equal to. So any operator, comparison operator there. And you can combine them with and or, of course. All right. Now, let me introduce how you would write it in the relational calculus along the way too. So basically, if you write it out in a calculus way, you can say that you want to select from relation R with where P is true, right? So there you will have that for all T that are member of R, you have the predicate T is where P is true. So if you write it out in the calculus way, it will be like this, right? Now, the second operator is called projection. So for projection, you would say you would project from relation and you list the attribute that you want to project, right? So basically, the schema of the result would not be the same as the input, right? Because it would only contain the fields or the attribute that you project. For example, if I have S2 here, I have SID, S name, rating, and age. And if I say project from S2, just S name and rating, then I will have the result of how many attributes? Just these two, right? Because I want to project just these two. So I have just S name and rating. But now, what it does is that if you use projection operator, it would also eliminate the duplicates. So for example, if I say project from S2 and only take the age, you can take a look that age from the original table will have 23, 24, 24, and 23. So the result would only be 23 and then 24 because the duplicates will be discarded. All right. Now, I talked about union compatible before, right? The word union compatible. Now we'll take a look at what it means. So I have here union, intersection, and set difference. They actually require the property called union compatible. Whether it be intersection or set difference, they all require that it has to be union compatible. So basically, what it means is that for union compatible, you have to have the same number of attributes. For example, if you want to union the two these two relations must have the same number of attributes. Say you have 5 attributes on both sides. Okay. Now, I'm not saying that they have to have the same name. All right. First rule is that same number of attribute. But now it doesn't have to be the same name, but the corresponding field or corresponding attribute must have the same type. What it means is that attribute number 1 on one relation has to have the same type as attribute number 1 on another relation, right? Okay. Again, name can be different. So schema of the result will be equal or be same as the schema of the inputs for sure. Let's take a look at how it works. Okay. Let's see that I want to union R and S, right? If I write it out in calculus, I show it here, R union S here. You have T that is member of R or T member of S, right? Now, S1 and S2 here, if I union it, you can take a look at these 4. There are 4 attributes there in S1 and 4 attributes in S2, right? Now, this is like union compatible rule number 1. Union compatible rule number 2 say that corresponding columns or corresponding attribute must have the same type. Now, this one is easy because it's SID here, SID here, so we know that it's the same type. S name here, S name here is the same type. Rating and age is also. But let me change it here. What if, okay, what if I switch rating here and S name there? Would it be union compatible? Would it still be union compatible? Of course not, right? Because the corresponding, I mean, number 2, attribute number 2 here has to have the same type because it doesn't have the same name, but it has to have the same type. And here, you have to have the same type. So if I switch, name is actually string, right? And rating is integer. So it's different type if I switch. So it wouldn't be union compatible in that case. But now, let's go back to this example, it is still union compatible. So we can union it. So the result, ooh, okay. So the result would be the union of S1 and S2, right? Now I have 3 there, I have 4 here, but how come there are only 5 here in the results? Because if you have duplicates, duplicate will be discarded, right? So instead of having 5, there are some of the rows that look the same, exactly the same. So basically, you have this 31 here and 31 here. You have 58 here and 58 here. So they are, one is discarded. So you have just 5 there. Okay. Now, can we union S1 and R1? Here I have R1. I have SID, BID, and D. Can I union S1 and R1? Never, right? Because it already broke rule number 1 where you have to have exactly same number of attributes. So it's gone, right? Yeah. Okay. Now, let's go to the next one in the intersection. So actually, I told you about the basic operator that make up the additional operators, right? So intersection is actually R intersection S is actually equals to R minus S. So in that case, you can have this intersection instead of writing out this whole thing. And if you want to write out in the calculus way, it is where R intersect S, you have all the T uh, which are the member of R, and T as members of S. So basically, in this case, if I do S1 intersects S2, what it means is that it has to have the member on both sides, right? So I have 31 and 31 here, the same. This one is set as answer, and I have 58 here. But I don't have 22 in S2. I don't have, oops. Uh, and I don't have 44. So basically it has to have member in both on both sides, right? Whoops. Okay. Now, set difference. If you take the set difference, it's actually where T is member of R and T is not member of S. So basically, if I have S1 and S2 here, and I said I want S1 minus S2, what would be the answer? You actually have the answer on your slide, right? But I'm just going through this with you. So basically, if you take S1 and minus S2, you will have you have 22 here, which does not happen and does not show on S2. You have 31 there. So 31 would be discarded, right? Because you do set difference. You have 58. So 58 would be discarded because you have them on both relations. So because S1 is it's on the left, then you only have this 22 as the result. However, you know that mathematically r minus s is not equal to s minus r. So this is just the basic rules. Now comes the cross product operator. So basically what cross product does is that it would return all possible combinations of the row in R and the row in S. So basically on both sides of the operator. So I say R times of cross product S, you will get all the T in Q where T belongs to a member of R and Q member of S. So the result would be every possible pairs from R and S. And then there are some assumptions here. I said that assume that attributes in R and S are disjoint. So it means that R member in R and S is not the empty set, right? So if attribute names in R and S are not disjoint, we must rename them. So let's see what it means by that. Let's see the simple cross product first. So I have R1 and S1. I will, oh, อันนั้นมันหายไปแล้ว When did it happen there? Try again. Let me know if something happened like that. Sorry, I didn't take a look. Okay. So if I have R1 and S1 here, I'm not saying anything about union compatible, right? So when you usually, let's take a look at the meaning of why we need to cross product. Because if you want to combine something, you combine different relations and they do not have the same schema, right? They do not have the same schema. So you cannot union it. You can only union because only when it is union compatible, then you can combine the two tables together. But when they are not compatible, then you have to combine the table via cross product commands. So let's see what happened there. If I take R1's cross product with S1, you can see that I have SID coming from here, BID coming from here, I have day coming from here. And from it for S1, I have SID there. I have S name. I have rating there, and I have age. So you will have the result that came from the initial tables. So those two initial tables have 7 attributes altogether. So the results would have 7 for sure. Now, when we talk about the tuple, it will be every pair. So it will be like a mess, right? Because if you take a look at this, then I have these 22, this line coming here. And then I have to combine with the, let me change the color a little bit. So I have this 22, right? 22. So I have to combine those first line followed by the first line from the second relation and so, right? So then the next I have to do 22 there. And I have highlight here. Let me change the color there. You can see that you have to combine every possible here. All right. Now, so these 22 from first tuple on the left side, we'll go there. And then on the second one, will be here. All right. So you have to patch everything from there on the left side, which come from the first table or the first relation, and the right one would come from the second relation. So now you have all possible pairs together. So basically, if you want to know how many lines there are, we'll call it, there are 2 terms here, cardinality and degree. So for cardinality is the result of how many rows there are after you cross product. So let's say that I have like A cross product with B equals to C. So the cardinality would be number of rows. So how many rows? So you have to use A minus, so there are 2 rows from R1 and 3 rows from S1. So you have 6 rows altogether. And then for the degree, it is the number of attribute or number of columns. You will take the degree of A plus the degree of B, right? So you will have 3 and 4 here. So you have 7 columns altogether. So if I ask you cardinality, it would be number of rows in the results. If I ask you about the degree, it would be number of attributes in the table, right? Now, I want to the composition of operation. I want to compose different operators together. So first I have R1 cross product with S1. Okay. And then what I want to do next is that I want to do R1 cross product with S1 here, but I want to select. Remember, select, right? But I want to select where R1 dot SID equals to S1 dot SID. So what it means is that after I have the result of the cross product in the first table here, I will only select where R1.SID, so this is this column, equals to S1.SID. So for these, I only have this set 22, 22, and I have, so the rest 22 and 31, I will not take it. 22, 58, I will not take it. 58, 22, no. 58, 31, no. Then I'll take 58 and 58 here. So this is the result where you have cross product followed by select. And this is actually the operator join. What it does is that the operator join will cross product and then select just the row where the comparisons of what you want is there. So we'll go over different joins that afterward. All right. Okay. Again, you can see that when you do just the cross product, like the one on the top right here, there are a lot of errors, right? A lot of how do I say, the data that should not be there. For example, this line here, SID is 22, but how come you have SID 31 on the same line? You can tell that this one is not going to be correct in the table. That is why we always do the cross product followed by something, and usually it is cross product followed by select, right? Now, there is another operator called rename, which actually will be used in the join as well. So let me go over how are we going to rename attributes or relation names. So let's say that if I have a relational algebra expression called E here, okay, the way to rename, there are so many ways to rename attributes and also the relation name. It will, once I issue the operation row or operation rename, it will return the result of expression E under the name X. So E would become X here. All right. Now, that is the name of the expression E, right? Whatever the expression E is, you will see the example soon. However, if you want to rename just the attribute, here's how to do it. To rename just the attribute, you can do this. You can say that old name here, and you change it to new name using this arrow, the right arrow. So the right arrow will give you the new name. But you can do it differently as well. Instead of saying O name, you can say position of the attribute. You can say like position number 2, whatever name it is, will be changed to the new name, etc. And then you can combine all those renames all together. Let's see the example. Okay. Oh, by the way, there are some alternative notation where I have the E. After I rename it here, it will become the new name X. And I can also just list all the new names. But if you use it this way, the number of new names will be equal to the number of attributes. So every attribute will be renamed to the new name, but you can use old name as well. But I mean, like position number one will be renamed to the first position. All right. Now let's see the example. So I said, I have an expression called r minus s, and I say that when r minus s is done, or this operation is done, keep it in the new relation name called my relation. And also, if there is an attribute called a, please change the name to e. And for attribute position in the second position, change the name to k. All right. And the result will be on the right here. So I take r minus s, and the result will be kept in the new name, my relation. So these result, you can use this result afterward because it's already named my relation. And then the result from r minus s will be kept in there. However, you can also see that if there is an attribute called a, so you see that you have a here, right? It will be changed to e. And for the attribute in the second position, which is b, please change it to k. So actually, this command or this line is not really good because you use it two ways, right? So instead of like A change to E, I can also say A change to E and B change to K. Or I can say one change to E and two change to K. All right. But I just want to give you like different examples here. So that is another way to do it, is that I said in the result of R minus S, keep it in my relation. And I list all the names of the attributes that will be kept in the new relation. All right. Okay. Now, so we talk about join, and we'll be talking about join a lot after this. So join or with a ribbon is one of the most useful operations. You use it a lot when you want to combine relations that that are not union compatible. Now, so join is always cross product followed by selection and sometimes projection, but it's not required. At least you have to have selection. You could have projection, but it's not really necessary. All right. And again, the reason to use join is that because if you use cross product, it's actually meaningless and it produces a lot of waste storage. There are three different joins that I want to talk about. They are called condition join, equijoin, and natural join. Let's go to the first one first. The condition join, or called theta join, how you will write it is that you would have R condition join with S. So when we say condition, there must be some condition there, right? So when I say condition, let's see how we do it. I can write R1 join with S1 with some condition here. So condition here say when you join it where R1.SID is less than S1.SID. It doesn't make much sense, but I just want to show you how it is going to be calculated. So if I do R1 join with S1 where only R1.SID is less than S1.SID, what happened is that first it will take the cross product, right? So after cross product, you have all those 6 lines. Let me go back to this page. Okay. Erase. Okay. If you take just R1 and you cross product with S1, you have these 6 lines, right? But now I say, I want to select where SID here and SID here. I want to say that it is less than, right? So the result would only be these 2 lines where 22 is less than 58 and 22 less than 31, and the rest do not meet the condition. So the result would show just these 2 lines. All right. So this is called the condition join. You can put any condition. You can state any condition here. So you can have like equal to, greater than, whatever that mathematical comparison there. Now, the next one is called equijoin. Equijoin is actually a subset of the theta join or the condition join where the condition can only be equals to. So if you remember, when we do the condition join, you can have anything, right? Any condition at all. But now for equijoin, as its name implies, you can only have the equal operation. So basically, if I do R1 joined with S1, I want SID on the left side equal to the SID on the right side. So it means that I can only say SID because the condition is always equals to. All right. So when I say equal to, then the result would be R1 and S1 here, when you don't have like the 6 lines there, and you only select the line where SID on both sides are equal. So the result would be this 2 lines. However, you have to note here that how many attributes are there on the result here? How many attributes? There are 5, there are 6, right? But when you do R1 cross product with S1, how many attributes were there? Here. If you have R1 cross product with S1, how many attributes? What is the degree? It will have to be 7, right? But in case that you do equijoin, it means that the condition that you use must be equal to, so you eliminate once that pair to only show one. So SID would only be shown once. You don't duplicate the SID twice because it will be equal to, so you don't have to show that. All right. So from condition join to equijoin, let's do it again. So with the condition join and equijoin, the condition join is like more powerful because you can have any condition. But then for the equijoin is only equal to, right? So then one of the pair will be discarded. All right. Now, the next one is called natural join. Natural join is even further specialized. So when we do the equijoin, we'll take a look at both relations that we are going to natural join them and see how many pairs have the same name. And you join every pair with the same name, all right? Okay. The descriptions here are very long, but what it means is that you join every pairs with the same name. Let's take a look at this. I have relation A on the left side here, and I have relation B here. I want to join them, right? Let's take a look at the first one. Do you think can I just union them? Can I union them? They have 3 attributes together, right? But do they have the same type? Let's say that if age is integer and ID is string, you cannot join them, right? But let's say that if age is also integer and ID is integer, can you join them? Are they union compatible? If age is integer and also ID is integer, can you combine them? It is union compatible, right? But the meaning will be all wrong because you will be joining age and ID in the same column. So it will be all wrong, right? Now you want to cross product and select, but let's see how it works. So you have 6 tuples on the left and you have 2 tuples on the right. Of course, you know that the result would have 6 tuples altogether when we do the join, right? But now with the natural join, I said that let's take a look at how many pairs there are with the same name. With the same name, attribute names, you can see that it, L name here on A, L name here in B, also F name in A and B. So now you have to join both of these attributes. So basically, let's see the result. I said that both L name and the F name match. So select, and then you put it here in the result and take a look at, see here. L name and F name. L name equal to F name equal to. Now, on the second line, L name is not equal to L name on the right? So these are not equal. You will not take it. And then on the third line, L name is equal to the right one, but F name doesn't match. You don't take it. So you end up with just one line in the results. So we remove, and plus that you have to remove all the duplicate attributes. Therefore, the natural join of A and B would only have L name, F name, age, and ID because L name would be discarded, just one. F name also duplicate, so just take one. So now you have L name, you have F name, you have age from here, and ID here. All right. So you have to join all the same name. And this is why the rename is important, because if you want to join more than one set or any set, you have to make sure that they have the same name so they can join when the two relations from both sides have to pair with the same name. Right? Okay. Now the next operator is called division. For the division, it said it is not supported as primitive operator, but useful in expressing queries like find sellers who have reserved all boats. Or basically, what I like to use is like if I want to find students, okay, if you are taking course in ICE, right, and I want to find any student or every student who earn A in all classes that they take within the program. Okay, let's say that there are like 50 classes that you have to take and you get all A's. Then what you can do is that you can use the list of all the courses and you use the division operator to identify just the students who can get all A's from those lists of courses. All right. Now, I also show you how to write down in relational calculus there as well. But let's take a look at how it works. I have relation A here. And now what I want to do with the relation B1 is I want to do A divides by B1. So how it works is that we take a look at B1 and say, well, let's take a look at B1 and say B1, we have P number equals to P2. So we take a look at the A side and see which S number has P number as P2. So I say, okay, we have P2 here, P2 here, P2 here, whoops, and P2 here, right? This one goes here. Now, so the result would be, okay, the first P2, we have S1. So S1 is the result. The second P2 is S2. The third P2 is S3. And the fourth P2 is S4. So that is the result when you have A divides by B1. Okay? Now, let's take a look here. If in my B2, I have P2 and P4, what would be the answer? The answer is actually on the slide, but how it is computed is that you take a look at P number here and P number here. I want the whole set P2 and P4, where S1 has the same, S number is the same, right? So I said, okay, I have P2 and P4, where S is the same, so S number is S1. And then I have P2 and S2. Do I have P2 in S2? No more, right? But now I have P2 in S3, but I don't have P4 in S3. But I have P2 and P4 in S4. So that's why the result is S1 and S4. Is that okay here? You're still okay? Okay. All right. And finally, let's take a look at B3. If I take A minus A divided by B3, then you have to take a look at P1, P2, P4 with the same S number. So I have P1, P2, P4, where S number is S1. but I don't have anymore. I don't have P1, P2, and P4, where S2, S3, or S4. So the result would only be S1. So this is how the division operator works. Okay? And the next one is called the assignment operation. For the assignment operation, it's actually you want to create a temporary results in a relation because you want to use them later on, then this assignment operation would be very useful. Let's see how it works. All right. For example, here I said that, okay, I want to write a minus a divides by b. So what I do is that I take this expression and I say assign it to term 1. It doesn't matter what is on the right, but you take the result from whatever on the right and keep it in a relation called term 1 on the left here. And then the usefulness of it comes later where you use term 1 there. Now you can use the name term 1 because you already created a relation called term 1. And then I said, well, from term 1, I want to project X and keep it in term 2. So you create another relation called term 2. And now you say that the result is you project something from A, where with X, and then you minus term 2 there. So what it means here is that you want to keep the results somewhere. And somewhere means some temp relation. And you can use the assignment operation where you write it as left arrow. Okay, you use left arrow to assign a temporary relation that you want to use in the following operations, in the following lines there, right? When things get very complex, the assignment operation will be very useful. Okay. Now, there are some other operations that will be quite useful as well. So they are grouped as aggregate function and outer joins. When you use the aggregate function, we'll use the F script. This is F script as function, right? In F. And then when you write an F script, you say this is expression E, whatever it is, like R minus S, R divided by S, whatever it is, like cross product and so and so. And then what you do is that you can say function 1 of attribute 1, function 2 of attribute 2, or function n of attribute n. And also you have something in front of F script, which are groups, like group by this G1 attribute or G2 attribute, or group by whatever attribute that you are interested in. So basically, the aggregate function would become very useful. Okay. Because these are some of the collections of functions that you usually use, like average, min, max, sum, count. They are used quite you use them a lot. So what we do is that instead of writing out just like each function and you have to write very long expression. These are the function that would help when you write out the operations quickly. So basically, E here is any relational algebra expression, and G is a group, and F is a function like min, max, average. Let's see how it is used. All right. So if I have a table R, a relation R on the left side, I have A, B, C there, and I write down F script here, and I said the relation R, I want to sum. Sum what? Sum attribute C. So the result would be the sum of whatever in column C or attribute C altogether. So that's why you have 27 as the result. However, if I say I want to sum C again, but I want to group it by A, okay, by A. So A is this attribute, right? So I say, what I mean here is that let's group where A is equal together, and then you group them like alpha together, you group beta together, and then you only sum each of the group. So the result would be the sum of all the alpha and the sum of all of the beta there. Okay. You can specify more than one group as well. So the calculation would be done according to whatever you specify. Okay. Now, another one is called outer join. You remember the join, right? How many types of join that we talked about? There were three, right? We have condition join, we have equijoin, and we have natural join. Now we talk about other type of join. Why do we need this? Usually those three will only have the results that come from both sides, right? But now, if you want to maintain all the data in the table on one side or both, then we'll use another command called outer join. Let's see how it works. So it would compute all the joins and then it would add the tuples that you want to maintain. However, there might be some of the information that's not exist after the join. Okay, then you will use something called null to specify that there are some values that does not exist. When some values that does not exist or you don't know whether or not it's there, like an unknown value, or if that does not exist, we'll patch null. So don't ever use like space or use zero because those are values. When there are no values, it is called null. All right. Let's see how it works. I have table called loan here. I have table called borrower here. So what I do is that let's see that I have loan number, branch name and amount in the relation loan, and I have customer name and loan number in the borrower relation. So you only have these two match, right? Loan number here in loan and loan number here in borrower. So you know that for loan number here, it belongs to this branch and this amount. But if you want to know the name of that loan number, like who belongs to that loan number, who is the customer of that loan, you have to take a look at the borrower table or borrower relation. So what we do here is that I still have these two on from the previous slide. And now if we do the inner join, if you remember, we do inner join. So I said loan join with borrower. What it does is that it takes all the pair with the same name, right? Set pair with the same name. I have this loan number and loan number here, and it came to this loan number. So this loan number actually will be discarded, but I have branch name, amount, and customer name here. However, what I do is that you would notice that these 170 came here, 230 came here, but we lose that 260, right? So information from some of the lines would be discarded because they do not fit with the inner join. Now, what outer join does is that you want to keep one side or the other or both. So let's take a look at the left outer join first. So for left outer join, I said that I want to maintain every data, every tuple of the data from the left side. That is called the left outer join. So whatever it is on the left, keep every tuple. Okay? So when I keep every tuple, you can see that 170 comes here, 230 comes here, and also 260 comes here. But now, after you join, what would happen? Because the 260 on the left does not have any information on the right. So you have to patch null. You have 260 Dublin 1700 from here, but then you cannot match anything from the borrower because you can't find 260 from the borrower. So you have to patch null. All right. This is how null is used when you do join or when you do anything that does not have the data there, unknown or does not exist. So you patch null. Okay, so the same thing will be done with the right outer join, but at this time, you keep anything on the right side, right? So let's say I have loan, right outer join borrower. So I have to keep everything from borrower. So I have customer name here, I have loan number here. So loan number 170, 230, and 155 will be kept. And then you cannot find 155 on the left, right? So you have to patch null, for branch name and amount. Okay. All right. Now, the reason that it is the attributes on the in the results will be loan number, branch number, amount, and customer name. They are ordered by these operation. It said loan, write out a joint borrower. So it have to take loan first. From loan, you have loan number, branch name, and amount. And then you write out the joint borrower. So borrower will be uh up because so the customer name came here. All right. Now you can also have something called full outer join. So you keep both left and right, and then you patch null anywhere that the data does not exist. All right. So outer join, there are three ways. Left outer join, keep anything on the left, everything on the left. Right outer join, keep everything from the right. Full outer join, keep both tables all together, but patch null where data does not exist. Okay. I'm pretty much I have a lot of time because I can finish it by 10:30. So you can talk about the project later on. So usually I lecture this in 1.5 hours. So yep, I'm in time. All right. So the relational calculus is basically another formal language as well. And it operates on relational model, same as relational algebra. But the way we write it, as you see that I, tag that along, is that it provide a decorative way to specify the queries, right? Where again, the relational algebra is in a procedural way. So you do it procedure by procedure or one line by line. So they are logically equivalent, right? So for any algebraic expression, there must be equivalent expression for calculus and vice versa. So let's take a look at the example here. I said that I want to retrieve the phone numbers and names of bookstores that supply Harry Potter. So I have the first relation called bookstores. And for bookstore, I have bookstore ID, store name, address, city, zip, and phone. So if I want to retrieve phone number, I have this phone number here, right? And I want the name of the bookstore, store name here is what I want, phone number here. But I don't know which store supplies Harry Potter, right? So because this is the relation for bookstore, I don't know if it has the Harry Potter. So now I have another relation called book. Well, for book, I know that which bookstore have this book along with its ISBN title. So now I have title Harry Potter that I wanted here in the book relation. And I have other information like type, author, price, and publisher. Now, if we are going to write a relational algebra expression to retrieve phone number and name of bookstores that supply Harry Potter, basically, pseudocode would say select from book where title equals to Harry Potter, right? So no bookstore ID that has Harry Potter. And then you join this bookstore ID together, and then you will be able to project the result, just store name and phone number as it required by the question here, right? Now, if you want to write a relational calculus, okay, you can write it like this. This is just a pseudocode. You say get store name and phone for supply such that there exists a title with the same bookstore ID value and with a title value of Harry Potter. All right. So the result would be exactly the same. So let's take a look at this example. I said, I want to find the names of all customers who have a loan at the Riverside branch. Okay. I want to say, I said all customer names of all customers. So I want customer name. But in loan, we know that there are loans in branch name Riverside, but we don't know the customer name. So you have to join them anyway, right? Now, if I write it out as relational algebra, it will be something like this. So I take borrower and I cross product with loan, and then I select where loan number from borrower is equal to loan number from loan table. So basically this is, what is it? So this is a join, right? Okay, let me ask you, if this is a join with equijoin, condition join, or natural join, which one? The way I write it is actually condition join, right? Because I specify the condition equals to, but if I want to write it as equijoin, how would I change it? I don't have to say borrower dot loan number or loan dot loan number. I can only say loan number. And then it will take a look at both sides to just match the loan number on both sides, right? Okay. Can I say natural join without saying anything? Can I? I can, right? Because it will take a look at the pair with the same name. So it say, oh, loan number are the same on both sides. Then let's join loan number on both sides. All right. This is the difference. Then I said I would only select where branch name equals to Riverside. And then I project the result, just the customer name. So this is how we were going to write. It could be, you could use join as well. So this is just to write out with basic operations, right? If you are going to write it with calculus, it would be like this, right? You do, you want the result in X, right? And what you do is that you have to write what you want, right? So you said you want all customer who have loan at Riverside branch. So here you want borrower, and you want ABC, and ABC would be the member of loan, and B from Riverside, and Y equals to A, something like that. Okay. Now, to sum it up, I said so many times that relational model, is really simple, and they are very powerful when you want to retrieve the data from the database. And again, the relational algebra is operational, while and it is very useful. Here I said internal representation for career evaluation plans. Why do I say that? Because if you know step by step how the operation would be executed, you can then write different plan. For example, you know that this when you write out SQL commands, you know that there are many ways to write out in order to retrieve the same results, right? However, the way that you write it could be different in terms of effectiveness and how it is powerful, or it makes it faster or slower when you retrieve the data, especially with very large table. So now, if you write it out in algebra, you know exactly which line or which command actually makes it bad. For example, makes the operation runs slower, then you can change it just one line or the other. But if you write it in the calculus way, it is not possible to change the execution plan, right? So this way, the something called query optimizer will be the function or the feature that you see in every of the DBMS. It is called something called query optimizer, which actually will take a look at the expressions from relational algebra and try to optimize how the table will be run according to all those SQL commands that you issue, right? Now, again, the relational algebra and relational calculus are essentially logically equivalent. So that's, yep, I have finished it in just half the time. Yay! Okay, so any question on relational calculus and relational algebra? Me, ma? If not, what we can do now is that we can take a break for like 10 minutes. And if you don't want to take a break, then you can come talk to me about the project as well. You go home. If you don't have any question, then we'll finish it first. Okay. Anyway, let me remind you that for if you take a look at the assignment, you will see have exercise 1, 2, and 3. So 1 and 2 are due yesterday, and we will post the result. We'll post the answer key for you, and then there is a new one, exercise number 3, which is out today, and it will be due next week. All right, and again we'll post the results for you to check, and then last time, after the milestone number 1, we told you about the optional bonus point. So basically, what I would strongly encourage you to do is that once you submit your homework, the assignment, then you take a look at the answer that we will give out. Now, the answer will not have just one correct answer, right? There can be many correct answers, because it's a design class. So what you can do is that you can evaluate your result and you say that, oh, this is not the same, but I think mine is better. So you can write it out in the discussion section here. So I have the discussion section for both of the exercise already. So you can click there and then you write out, okay, mine is like this. I think it's better. Or if you think that your result is wrong, you can also say something in the discussion, say that here is my result and here is how I fix it. All right. So just do anything meaningful. And then what happened to obtain the bonus points is that you can just pick one that you think is most meaningful and you capture that by the end of the semester, and then we'll give you those 3-point bonus. And I have other good examples and bad examples here. And for example, here, like my answer is different from the key. I decompose the relation this way, but actually this one is okay. So here's my reasoning, things like that. This one is very useful when you are reading other people's answers as well. I mean, not answer, other people post as well. You can also take a look at your friend's answer and then argue something. For example, you said that, oh, my answer for this particular exercise is already correct, so you don't want to say anything, but you take a look at your friend and say, oh, this one is useful. You can also analyze your friend's work and give some opinions on your friends, so it doesn't have to be from your own answer. Okay. Here in the discussion, yes, it's not required, but if you do it, will get the extra point. All right. But it is not required. But you know that 3 points can change grade, right? That's that's something meaningful there with the 3 points there. So you can do it. It's optional, but it's you earn extra points. But we do it this way because we want to encourage you to take a look at your friend's answer and analyze it. So it's a good exercise there. All right. Okay, so yeah, two things I'm pointing out where the assignments are and also the discussion board there, and then you can use them accordingly. And also, if you want to take a look at how the bonus points work, you go to the announcement. It says optional bonus points +3 here, and the details are written here. All right. All right. Okay. So let's take a break. And then if you want to talk about the project, you can come see me. Otherwise, you can take a rest because you have another class in the afternoon, right? All right. So folks from Zoom, bye-bye. I'll end the recording now.